Okay, we've just understood that there's two different ways of describing fluid motion, either in terms of an Eulerian description or a Lagrangian description. There's going to be several different ways of imaging that motion and showing it. And again, a very good place to look is the movie by John Lumley on Eulerian and Lagrangian descriptions. And there are also many beautiful visual examples online that you can find on YouTube or in a resource called Multimedia Fluid Mechanics Online. But several of the ways that we might describe things are going to be what we'll talk about today. And the most important one that we'll use a lot is the idea of a streamline. And a streamline is, as I've shown here, is by definition everywhere tangent to the local velocity field. So we can see that this is really defined in reference to an Eulerian description, because we need to know the velocity field at a particular point. And the equation of our streamline that we might write, which I've indicated here in green, we might write as the following, that an equation would be that if it's everywhere tangent, then by laws of similar triangles, then we would write that along a streamline, the following relationship is true. So x and y are independent variables in space in general, but the particular coordinates with a subscript s indicate the equation of this line where we're following a streamline, which we might label by its location s. Of course, it can be defined in 3 dimensions, and we know that the velocity field may be varying in time as well. So in general, these are complicated time-dependent functions, and so the streamlines also change in time, but they're very useful. So they're most useful for steady flows, and they're particularly useful for steady 2-dimensional flows. So we'll often draw the streamlines to represent a flow field. A couple of things that we should recognize is that streamlines shouldn't just end. So they're either closed, so we might be thinking about a flow in a complicated object that looks like that, or they enter and exit the flow domain. So, for example, then they're a very good way of representing boundary conditions. So if we have, let's say, flow in an object that looks like this, then we might represent the flow in terms of streamlines that we are very careful to draw as entering the flow domain and exiting the flow domain. And then they give us an idea of let's be a little bit more careful in that drawing, shall we? They give us an idea of how the velocity field changes as we go through our flow domain. So that's one way of describing material, and we'll use those a lot. However, they're very, very hard to actually evaluate experimentally, except in certain conditions. And so we might also be thinking about other ways that we might like to describe things. And so a second way of describing things is in terms of path lines. Path lines are much easier to reveal experimentally, and it's basically just the trajectory of what we'll typically call a tracer, which faithfully following a local flow. So, for example, we might think about a little set of points in space, and we'd like to follow where they go. And the length of the path line, of course, depends on the exposure time. So, so the trajectory, so we'll say that the length depends on exposure time. Of my camera or my video. But once we've got those, then it's very nice that we can locally just say that the velocity field is equal to the displacement. So we'll write this as delta x over a time delta t. And of course, we're going to take the limit where delta t goes to 0. And this is, for example, how a technique like particle image velocimetry works. We'll seed the domain with a lot of points like this, and then we'll measure how the velocity field changes. So that's very useful as well. The final way that is useful for us to image things are called streak lines. And streak lines are indeed exactly what the name suggests. It's the locus of all material points that have passed through a fixed point in space. So we might specify that fixed point in space by, let's say, x0. And then we're going to reveal all the points that have passed through that by using, for example, injected dye. Or maybe smoke, or maybe small hydrogen bubbles. And so if we were to try and draw a representation of this, then we might recognize that we might draw a domain like this, and then we might use a syringe that we would inject. So we might insert a syringe with a dye inside it, and then we'll inject a dye, and we might follow where that dye goes in time, and then we might use a different color syringe somewhere else. We might inject a different color dye, and we might follow where that goes as a function of time. But the key thing is to recognize is that in each case it's going through a fixed point in space, and we're imaging the flow downstream of that. Now, in general, these all give different descriptions of the flow field, and the results may look slightly different, with the one key exception that in a steady flow, then we'll find that the streak lines allow us to reveal the streamlines. And so we'll use this a lot going forward. The final thing we'll note about these different descriptions, we've learned about an Eulerian and a Lagrangian description. As Lumley points out in the video and shows very nicely, one of the key benefits of an Eulerian description is that very frequently it's possible to see a change in the reference frame or find a change in the reference frame such that the flow becomes steady in that reference frame. And so then in a steady reference frame we might find that we can easily image streamlines and streak lines, and then our velocity field will no longer become a function of time, and so then this is just a steady problem, and this will mean that it's much easier for us to analyze, and so we'll see some examples of that in the next clip.